Hello everyone, I'm Semih Burak from Aachen University. I'm a research associate and PhD student at this university, and today I'm here to talk about my paper SPMD IR, Unifying SPMD and Multi-Value IR, showcase for static verification of collectives. And the motivation basically is that the HPC systems get more complex and heterogeneous, and not only the hardware, but also the software. And for effectively utilizing this HPC clusters, we have different program models, and for example, inter-node communication and SPMD-like program models, such as MPI, are unavoidable. And although we have different program models, they have distinct specializations, but also common features. So here we see, for example, MPI, we have OpenSHMEM, or called SHMEM, where we have a PGAS memory model into it. And then we have NVIDIA collective communication library, which allows us for GPU to GPU communication, and possibly other program models. And the problem here we have is that we have different tools where one of them possibly only supports MPI, other tools supports maybe multiple program models, but the necessary abstraction is incorporated directly within this tool. So if we want to have another tool which also wants to support multiple program models, or if we want to support which is called multi-value analysis, which I come to in a minute, then we would need to spend again the same effort. And to avoid this multiple efforts, the idea is to reflect the abstraction and multi-value analysis in an intermediate representation called SPMD IR, so that other tools can just work on this SPMD IR, and if they implement their analyze optimization onto this SPMD IR, then all the program models that can be converted to this intermediate representation will be supported by these different tools. So the remaining of my talk, I will first introduce MLIR, which is a framework and also important for the concept for my intermediate representation. Then I will talk about multi-values and the extended about multi-values. And then we'll go over to the main part about the SPMD IR, where I first talk about the extended multi-value analysis which we implemented. Then we'll talk about the scope. Then we go through an example, and then the implemented workflow. For the evaluation, we chose the use case of static verification of collectives, and we'll compare our approach, or more or less on our tool chain, with a tool called ParCoach. And lastly, we will discuss certain limitations we spotted. So first, MLIR, it stands for multi-level intermediate representation. It is published 2021, and it builds upon and is part of LLVM. And generally, the purpose of intermediate representations is to facilitate optimizations before we lower them to a low level or even machine code. And if you compare LLVM IR, which is probably common also to you, with MLIR, then we can say that MLIR is more extensible, reusable, and we can mix low-level and high-level abstractions. So basically, we could have an MLIR representation where we have LLVM IR low-level operations next to high-level ones. And the one benefit of MLIR is that we can encapsulate domain-specific information into so-called dialects. And the dialect is a collection of custom operations, types, and attributes, and allows us for encapsulating any specific domain information. And another benefit of MLIR is shown here. So we have different programming languages, for example, C, C++, Julia, and so on. And although they eventually get lower to LLVM IR, or can be lower to LLVM IR, they still use some custom intermediate representations over here. And these custom intermediate representations makes it necessary to re-implement certain optimizations or transformations. And if we use MLIR instead and build up our intermediate representation using it, we can save effort. And the idea is for now to express SPMD-related information in its own dialect and with a set of attributes. And we can use this dialect, which we will design, next to other special purpose dialects. For example, we could have one for shared memory parallelism. So here, one code example, an MLIR representation. So here we have in line 14, the func dialect, which is generally like red highlights the dialects, orange the values, and blue the types. And the func dialect allows us to represent or group function-related semantics. Yeah, for example, we have the func operation. Yeah, it's called also func.func, which represents a function. And here's the main function. And now, after we possibly define certain constants or other omitted operations, we have the memref dialect, which allows us with the alloc operation to define an array-like structure of size, and gives us a pointer like value, which stores the reference. And now we can use a call operation, which calls a function called multiplies by x, and the idea is that this function multiplies all positive values of an array by x. And if we jump over to this function multiplies by x, then we can have another dialect called arith, which can be used for arithmetic operations, or in this case for defining constants. Yeah, we define here constant 0. Then again, another dialect called SCF, structured control flow, which allows us to have high-level control flow structures. Here we have the for loop and an if structure similar to the C language. And in this loop, for example, we iterate from 0 to the argument size, the array size, by a step of 1. And the if operation branches depending on a compare result. And line 5 and 6 here basically checks whether it loads first the value from the array and then checks with a compare operation whether it's greater than 0. So basically whether the element is positive. And if it's positive, then we can use a multiplication operation and store the new value onto the array at the respective place. And yeah, you don't need to understand everything or every bit of MLIR or the code here, but the takeaway message is here that we can have different dialects, and each dialect can seamlessly interact with each other, and so we can provide, so MLIR provides a tool set to develop an expressive IR composed of multiple levels and semantics. Going over to multi-values. So a variable or value is called multi-value if its runtime value may differ for a subset of processes and called single value otherwise. Here an example. So here in line 1, we assign A to 13, and we assume that this is just nested into the main function. So we know all processes will execute this operation. So we know the value is the same for all, and so it's a single value. Here, MPI rank assigns the rank, and this is a special operation here, which is called MV-seed operation, which gives us a multi-value per definition. Yeah? Rank is different for all different processes, so rank is a multi-value. And now a conditional follows where it compares rank with 0, and we call this conditional multi-valued because at least one argument is a multi-value. And here within the conditional, we assign to A and B different values. And since it's nested into the multi-valued conditional, which is possibly not executed by all processes, here only by 0, those variables get multi-values. Then, in line 9, we have B assigned to 64. It gets a single value since it is executed by all processes, and B gets the same value for all. And lastly, we have C, which is the addition of A, a multi-value, and B, a single value. In this case, it leads again to multi-value because C is not same for all processes. So if we sum up, so we have MV-seed operations, which yield multi-values per definition. And new multi-values can result either from operations using multi-values. For example, the arithmetic operation here, A plus B, results in a multi-value, or through control flow operations, as we saw here. And now coming to the main parts, SPMD IR. So here we adapted an existing work for multi-value analysis, but for SPMD programs in MLIR, and add two kind of analyzer, execution kind, executing processes analyze. Then we express the results of this extended multi-value analysis in the IR by attributes, and those attributes are the following. First is multi-valued attribute, which tags the conditional whether it depends on a multi-value. Secondly, we have execution kind, and this specifies at compile time for each operation whether it's executed by all but, whether it's statically known which executes this operation, dynamic where the information is limited, or one and all but one. Then executed not by is a list of process IDs of as executing the operation, and this is given for the static and all but cases. So let's look at some examples. So here, basically, again, it's a code snippet, let's say, from the main function, and here we have the line 1 and 2, just an addition and assignment to A and MPI com rank, and we know both are executed by all processes. Then line 3, yeah, here it's this a comparison whether its rank is 0 or 1. So we know that the MPI barrier here is executed by 0 and 1, and we know this statically. Then line 7, the else branch of the same conditional, is executed by all but 0 and 1. In this example, we check whether rank is equals I, and here I is a single value, so it's a similar same for all processes, but we don't know at compile time what the value is. So the only information we have is that this MPI barrier is executed by maximum of one process. So that's why we say it's executed by one. And the counterpart of one would be all but one, and this would be the case for line 5. And coming over to the SPMD in terms of the scope, yeah, here generally we can say that that programming models such as MPI or others have certain concepts, features: process management, communicator management, data management, collective communication, point-to-point communication, or non-blocking semantics. And this is basically the list we currently support with our IR. So the idea is to have a minimal set of operations, types, and attributes that cover those features for unification purposes. So basically here for process management, we have like an init, finalize, get size of a communicator, the rank, or the device ID. Then we have for communicator management, for example, splitting of a communicator, the destroying, getting the world communicator. In terms of data management, malloc, realloc, or free. Then collective communication, basically all the different calls given in MPI. Then point-to-point, send and receive. And non-blocking, we have additionally the wait and test functions. And additionally, we use inherent attributes of the operations for differentiating blocking or buffered communication. And in terms of types, we use integers for process and device IDs or tags in terms of point-to-point communication. And we use the high-level memref type for communicated data, for example, the send buffer for broadcast or altogether. And then we use custom dialect types for the remaining. For example, a communicator would be of type SPMD-COM, and the same is for error values. We use the type SPMD error. And these custom types is among others for the fact that different program models such as Nickel and MPI have, Nickel has a more elaborate error handling, let's say, So this custom types will allow us in future to expand on this, which information we want to store into this value. Then I also want to make want to stress one point that for memory references, for example, let's say collective communication, we have a send buffer and a receive buffer. And here the IR also specifies side effects. So basically, we know at this point whether a buffer is only read or also written and so on. And I think the next talk from Team Yama will more go into the details of whether or of how these side effects or knowing these side effects and so on can help the compiler. Then we also had, before the talk discussion, remote memory access. One-side communication is not listed here because it's still a work in progress, and hoping it will come also soon. Then let's look at one example how this would look, how the SPMD would look like. Here we have a code snippet, C code, MPI, where we just get the rank. Depending on the rank, we do a broadcast. Obviously, this is just a code snippet. Otherwise, it would be a deadlock with only a rank 0 using the broadcast. But yeah, the same we could do in SPMM. Yeah, we could have getting the rank, then looking at 0, and then just use the SPMM collective communication core. Then in SPMD IR, it would look like this. Yeah, we have the SPMD dialect and the operation get rank and com, which gives us a rank. Yeah, the argument com, and then gives us a rank and an error value. Then we can use the ARID dialect for the compare operation, whether rank is 0, and gives us a compare result as a return value. And with SCF dialect, we can use the if operation for checking whether it's true, and then can execute the broadcast. And the broadcast gives as arguments the different important arguments, communicator, send buffer, and so on, and gives us an error value back. In terms of attributes, yeah, we have, for example, the execution kind attribute, which says, okay, this operation is executed by all processes. And we have additionally another attribute called use model, which tags or says whether an operation originates from a single program model. Yeah, if we, let's say, have MPI plus a nickel code, then we would have some operations with use model 0 and the others with 1. And this could be useful for code generation later on. And here again, this operation is also execution kind all, and the broadcast, yeah, it's a blocking broadcast operation executed by 0, and we know this statically. And yeah, lastly, the if conditional is also a multi-valued one. So in terms of workflow, yeah, we have currently C++ in front end and different program models, MPI, SPMM, and nickel as external function calls basically. We then use a tool called Polyguise for which allows us to transform in this C++ code to MLIR, but still the different API calls are external function calls, yeah, similar to LLVM-IR. So in the next step, we would have a unification pass with a transformer pass or a transformer for the different program models, which gives us the SPMD operations for MPI, SPMM, or nickel. Then in the second step, we have the multi-value analysis pass, which operates on this unified SPMD operations and gives us multi-value and SPMD properties or attributes. Then, after having done these two passes, we have now the fully SPMD IR, and now we can pass this to another compiler pass or a tool. Yeah, here we have, based on our use case, a collectives verification, but this could be also other tools. Then next we have the evaluation basically, and as we said, we use the static verification of collective communication as use case, and the idea is that we want to check whether the same kind of collectives, for example broadcast, has to be called or is called in order by all processes of the same communicator. Basically here an example, so we have a function f, and at some point it branches, and one branch goes immediately to this barrier, the other branch will do some stuff and eventually do also a barrier, and the other branch also. So basically these two barriers match, and but this one not, because there's one control flow pass which goes directly to this barrier, and this would be the first barrier on this pass, but for the other two passes, this would be the second barrier, so they are not matching. And if we now know that this conditional is multi-valued, then we know that not all processes will go on through one pass. So one process could go this path, and the others could go this or this. So some processes will wait at this barrier, while maybe the other would wait at this, and eventually it gets to a deadlock. So what we've done here is we have ported the tool, the approach of ParCoach, which does static verification of collective communication to the SPMD IR. and additionally implement two extensions. Basically, we no longer are operating LLVM-IR, which does ParCoach do, but we are now working on MLIR or SPMD-IR. And the two extensions we implemented is first to consider execution kinds of collectives induced by loops. So ParCoach basically reports an error as soon as you have a collective communication call within a multi-valued loop. And we differentiate basically dynamic with static cases. So if we know the execution and the count, then we use this for the verification. And the static one is for really static cases where the total number and executing processes are known for each operation. And this could be useful for target-specific code generators. And in terms of assessment, we compare ParCoach with our approach and use ParCoach micro benchmark suite for collectives communication, and additionally also implement some own custom test cases. And we also port all the MPI codes from ParCoach at their micro benchmark to SPMD and Nickel, and provide hybrid cases. So in terms of results, we have first a micro benchmark suite from ParCoach, and generally S stands for SPMD-IR verification and P for ParCoach. Here the true positives in green, in blue the true negatives, the false positives, and then there would be the false negatives in red. For MPI there is no difference. We have exactly the same coverage of the test cases. For SPMD, we can say that there was one test case not being portable to SPMD due to a limitation. ParCoach does only support MPI, so there's no support for SPMD or Nickel. In Nickel, we have one test case which led to a false positive at our SPMD-IR verification, and this has the following reason. So if we look at a simplified version of this test case, so we would have the Nickel rank and branching on it, and one would call the Nickel all-gather operation, and the other branch we would use the groups primitives for making it non-blocking. This is non-blocking, this is blocking. And if we now transform this to the SPMD-IR, then this would be tagged as blocking, and this was non-blocking. And the initial ParCoach algorithm would not match both. So as you know, in MPI we have different calls for blocking and non-blocking. So since there are different calls, they would not match and leads to false positive. So in terms of custom test cases, here the difference is that we have two false positives at the ParCoach side. And these two test cases are basically the representation of the two extensions we implemented. So we are covering these two extensions, but obviously ParCoach not. Then there's nothing special about SPMD and Nickel. So we have a similar, or the same coverage basically as for MPI, just that only for those test cases that could be ported to SPMD and Nickel. And also one strength is that we have support for hybrid test cases. So any combination of MPI plus Nickel or SPMD with MPI, so any of those will work also for the SPMD-IR verification. So the takeaway message here from the evaluation is that the SPMD-IR covers two test cases correctly where ParCoach failed to do so. And the SPMD indeed has one false positive for one Nickel port. And maybe the most important point is that we not only support MPI, but also support SPMD, Nickel, and also the hybrid combinations. So I want to stress a bit the hybrid usage of, or the strength of, or advantage of our approach. And here's an example. So in this example, we get the SPMD rank, and then in line 2 and 3, we ensure that the rank from SPMD and of MPI match. So even the world communicators are the same size. We have no guarantee that the ordering is same. So we need to make sure. That's why we basically create a new MPI conworld with the ordering of SPMD. And this is visualized with the assert here. But the important part begins here. So we have again a branch, let's say on the rank, and in one branch we do first a SPMD reduce, and then a broadcast, an MPI. and in the else in the else branch we do the other way around. And the problem here is then if we have a tool that understands only SPMD or only MPI, or maybe even both, it will not find the problem here until it also understands interaction of both. Yeah, so basically that both are using the same word communicator and same ordering and so on. And since we can analyze this statically or understand certain parts of it, when we convert this code to the SPMD IR, then the detection of this error is of same difficulty as for only one programming model. So this would be in SPMD IR, the same code. So we would just get the word communicator, get the rank of it compared with 0, and do in the one branch we do the all reduced broadcast, and the other one we would broadcast and all reduced. And the only part where it may be visible that they stem from different programming models is in the attribute use model. So basically for SPMD, I guess, is the use model equals 1, and for the MPI one it is 0. So there are indeed some limitations or points I wanted to discuss with you. So although our goal was to unify different programming models, we can say that the SPMD IR is rather MPI centric. And this has 3 reasons. So first, MPI is an extensive standard and program model, and MPI over time supports a lot of features which were maybe only formally given in other program models, let's say. Then it has obviously large community support, and that's why we also often chose the terminology given in MPI when we needed to decide, and is a de facto standard for discrete memory programming. Then the most API calls could be mapped to SPMD IR operations, but already certain differences between the program models made it difficult for the transformation. So let's look at the non-blocking semantics differences in MPI and nickel. In nickel or in MPI, basically the non-blocking information is given statically at the API call. Yeah, we have different calls when we want to do non-blocking. But nickel, we can store this information into the communicator and possibly dynamically. And if we have given this information dynamically, so we can't do the necessary transformation at compile time. Of course, we could do convert it or do some assumptions and so on, but yeah, it makes already the conversion difficult. Then we also unify the memory management, like PGAS memory management from SPMD, for example, with the non-PGAS ones from MPI. For our use case, it was no problem at all, but we need to observe this in future for other use cases. Then with all abstractions, there's some loss of information. And here, of course, we also have some loss of information. For example, multiple calls could be mapped to a single operation in the SPMD IR and so on. And and a similar case we saw with nickel that already to a false positive. Of course, we could, let's say, mitigate this issue with introducing, for example, an additional ID that distinguishes originally separate calls and so on. But in general, this would be contrary to the idea of unifying if we store all the information we had and so on. So this is kind of a trade-off. And I think the aim would be to at least find analyses or use cases where this degree of information is enough. And lastly, the execution kind and processes analysis is limited to a few patterns, static cases, and in future we want to expand on this. Then summing up my talk, so we establish a unifying and abstracting SPMD IR, which allows a programming model independent analysis and optimization. Then, and we did this for SPMD-like program models, including distributed memory, MPI, PGAS, SPMD, and GPU programs with nickel. And additionally, introduced a multi-value IR with the extended analysis for important SPMD properties. And we evaluated this on the correctness verification compared to the Spark coach. And we could outperform Spark coach in terms of programming model support, hybrid codes, and the 2 extensions. And we want to also stress that we did the first correctness verification for nickel, SPMD, and the hybrid combinations. And lastly, we extended the micro-benchmark suite we had from Spark coach and provided ports to SPMD and nickel and hybrid codes. And in future work, we want to extend the execution kind, executing processes analysis, and explore new use cases for the SPMD IR. Then we want to apply the SPMD IR to other program models, for example, NVSHMEM, maybe GASPI or UPC++. Then we want to integrate other SPMD features or paradigms, such as remote memory access, or even maybe OpenMP, for example, the work sharing constructs. And then assess the approach on more realistic codes. Yeah, so far we did this for the micro benchmarks and so on, but yeah, we want to go to proxy apps so we can assess it for more realistic codes. Yeah, thank you very much for your attention, and yeah, I'm open for your questions.
Yeah, thanks a lot for this great presentation and interesting topic. So, questions? Not so shy, guys. Yeah, come over.
I'm actually just curious about the proxy apps or realistic applications. Have you guys figured out a nice subset of things to trial? Because some codes might be not great for doing MPI, but that's how they operate, right? So they might be very inefficient. There might be optimizations they can do. It might be informative for them, but other ones might be like, a well-designed code that would just be good to test to your use cases, make sure you don't have any false positives or false negatives. Did you have a list that you're going through, or are you working on this right now, just trying to explore?
Currently, we have selected, I think, 3 or 5 proxy apps from, how was it called? HPC. Yeah, I forgot the name, but basically we chose a certain set of proxy apps. But yeah, you're right. There's a difficulty of, yeah. I mean, generally, like proxy apps ensure that at least the compiler side of our work is, let's say, on a better way to go. But yeah, the difficulty is that the proxy apps maybe only use a really tiny subset of MPI, for example, or use really rudimentary MPI, and so on. Yes, so it is. We need to see whether we can also cover this aspect, or we need to back this up with some, let's say, systematic micro benchmark suite, which includes all different kinds of MPI usage, for example. But that is a difficulty with proxy apps. So.
There you go. Thanks for the talk. I expect that one of the restrictions of the static analysis is that your view is limited, right? So you can only see the current translation unit in your current implementation. Is that right?
Yeah.
So if I have 5 files in my implementation, in my application, and they're calling from somewhere, I call a function that calls an MPI collective operation. You wouldn't see if actually everyone calls the collective operation, right? Is there a way to apply a whole program analysis with this approach?
Yeah, so basically, we already started with testing around with proxy apps, and then we started to also go in this direction you pointed out. There was micro benchmark codes, like one single file, and that's it.
Right.
With proxy apps, it's different. And yeah, currently we for the prototype, we use similar to link time optimization. So there's also the auto translation units would also be available for static analysis. But let's say you have a translation unit not available, or for some reasons and so on, or you don't want to have it available, then yeah, you would not know about that. And then any, for example, static verification approach would most often decide whether they want to have a false positive, possibly, or false negative. So they would just need to make a warning or so. Yeah.
Okay, thank you.
Yeah, thanks for the talk and the work. Very interesting. I was wondering if you have ability to work with subcommunicators or subsets, and if not, no, this is tricky. Do you have any ideas on how you're going to approach this?
So far, we did not. We don't support currently subcommunicators and so on. I also probably cannot answer right now how we would handle this.
on. So you mentioned also like for multiple programming modes now you have MPI style like. What about if you have threads? Is this also included in this SPMD IR then representation that you can handle if one or multiple threads calling MPI functions? So that they might interact because one uses a collective and the other not. So you would have a discrepancy. It's working in MPI because every process calls a collective. Thread is necessary to do this.
Yeah, basically, I think for the representation or transformation, this would be no problem because it makes no difference whether, let's say, if you have multiple threads calling an MPI API call and so on. So I think it would be no problem for the transformation. But there's the idea on the design of this IR, like currently, like for MPI and SHMEM and so on, there's an assumption or there's that, for example, the main function is called by all processes, right, and executed. And we could also see this as like having a for loop around the function and all the execution units are executing the function. And this would be then similar to OpenMP, right? So there was what I want to point out here, so that maybe we can also abstract even OpenMP work sharing construct in the same IR and try to see if we can do some analysis on that. But yeah, then of course it would change a bit how we look onto it, but yeah.